In the previous section, we derived least squares estimation, and we made some implicit and some explicit assumptions that we're going to start to unpack in the next few lectures. So what were they? Well, first, we're assuming a model that is linear in the unknowns. Slope m, slope and intercept m and b, parameters of a parabola a, b, and c. We also assumed that all the uncertainty is in the variable that we are regressing against. That is the variable we are trying to estimate. The y in y equals ax squared plus bx plus c, or the y in y equals mx plus b. We also assumed that we are minimizing that vertical distance between where that y value is and what the model predicts it to be. And we also assumed that we're going to minimize the sum of the square of all of those, which of course we did because that's what gave us that clean least squares solution. We also made some other assumptions that were not quite as explicit as those, and we're going to start to unpack them a little bit. One of the assumptions, not a particularly hard one, but one of the assumptions is that all the data points are equal. We treat all the data points as if they are equally important to us. And that makes sense in many cases. So how do I know that I'm treating them all the same? Well, because this is summing over all of the data points, summing the square. So the error from this point and this point and this point down here are all exactly the same. No points are special. And that's all fine and good, perfectly reasonable thing to do. But sometimes there may be certain data points that may be more valuable or more important or more reliable than others. So for example, you may care more about getting the model right down here near the origin and you're willing to have a little slop out here. Or you may trust, if this is a measurement you're making, certain measurements are more reliable than other measurements. And maybe you want to weight those, give them more importance to the fitting because either you care more about that part of the axes or because you simply trust that data more than others, and that's going to lead us to weighted least squares. So for example, in this plot, if I value these 2 points more for whatever reason, and I'm not saying I'm going to ignore everything else, but I just value these two more, well then this line would look very different. The fitted line now shown in red instead of yellow would look very different. Well, how would I do that algebraically? Well, I could take each of the errors that I'm summing over. So remember, each of these, everything in the bracket here is the error associated with one data point. And what I can just say is, well, certain errors have more weight than others. So I'm putting here a weighting, a W, just a scale factor, indexed on I because it's associated with each data point. And I'm going to weight each one of these. Now, obviously, this changes the error function because every data point now is not exactly the same. Now, what is the weight? That's not my problem as the optimizer. That's your problem. You need to tell me what are the data points, what is the model, and what are the weights associated with each data point, either because you care more about them or you have more trust in them. But once you specify the xi, yi, and once you specify the weights and the model, can we still solve this using the least squares machinery that we've derived in the previous lectures? So let's see what happens. So what are we going to minimize now? We've got wi, and let me just replace mx plus b minus yi with the delta sub I, which is the notation we've been using for the error. So what I want to minimize is the sum of the squares of the weighted errors. Well, let's try to get some intuition as to what's going to happen here. Let's imagine a sort of somewhat degenerate case. Let's imagine that the weights were w1 and w2, I'm going to set to 1. And I'm going to set the weights of everything else to 0. Well then, what will I have effectively done? First of all, my line will look like that because I'm going to draw a line through those 2 points, which is perfect. And essentially what I've done is I've reverted to least squares where I'm just ignoring the points x3, y3 through x6, y6. It's in the degenerate case, this is what would happen. And of course, the resulting plot looks completely different because I'm simply ignoring those other 4 data points. All right, let's see how we would now actually do this in our linear algebraic framework, because that's the framework we want to keep building on. So remember, let me just remind where we are. We've got our linear model, slope and intersect. I have my quadratic error function where I'm minimizing the square of the distances between everything. And now what I'm going to do is rewrite that in the linear algebraic framework. I've got my two unknowns, m and b. Here I've got my x matrix. Here I have my y vector. Remember, x1 multiplies m, 1 multiplies b. So that's mx1 plus b minus y1. That's the first value of delta in the summation over here. Next one, mx2 plus 1, mx3 plus 1, et cetera, et cetera. And so that gives, of course, rise to a vector delta that is equal to all of the deltas. No weights yet. We're going to put it back in a second. And then we wrote that in terms of a quadratic error function because what we want is delta transpose times delta, which is the vector norm squared. So our error in the unknown u, in this case we're back to a line m equals b, is just the vector norm of x, that's my x matrix right here, times u minus y quantity squared. All right. Now, what do I want to do is I want to weight all of those deltas. Okay? So remember again that this thing right here is delta. xu minus y is the vector of deltas. And then, of course, when I take the vector norm and square, I get the sum of the squares. So if I want to scale each of the individual delta components, which I've enumerated here, delta 1, delta 2 to delta n, I can't multiply it by a vector because that's already a vector. I need to multiply it by what? A diagonal matrix. So this is an n by 1 vector, and this is an n by n matrix where I've put in w1, w2 to wn in the diagonal elements. Let's make sure we understand what's going on here. Let's do the matrix multiplication. This matrix is, the matrix multiplication is this row, w1, a bunch of zeros, times delta 1. What is that? w1 times delta 1. Next row, 0 hits the delta 1, w2 hits the delta 2, of course, and then a bunch of zeros. That's w2 delta 2, and so on and so forth until I get here. I've got wn times delta n. So when I multiply this vector by a diagonal matrix, each component here gets multiplied by the corresponding element in the diagonal of the matrix. And now what I have is a weighted error function. Yeah? So what I have here is, I'm going to flip back here for a second. This error function right here, w is my weighting matrix, xu minus y is delta. I've got the quadratic over here, and now I have a slightly different error function here, but a quadratic, it looks error function nonetheless. Now we've got to make sure that adding that w in here is not going to cause us problems when we go to compute derivatives, set equal to 0, and solve. So now we've got the formulation. And remember, there's always these three parts to these regression problems. Come up with your model. That's on you to figure out what the model is. Specify the objective function. We now have a slightly different objective function than we did in least squares. We have a weighted objective function. And now we've got to turn the crank to figure out how do we find the parameters, u, that minimize that. And the hope, of course, is that that adding of that w matrix hasn't caused any problem. And we'll see what happens next.